Greetings everybody, and welcome back to another exam solution video. So I've done the multiple choice questions for exam 2 of 2021. So now we're going to do section B. So I've already done like 2 questions I think last year. I posted those videos, but those are really crappy videos, so I'm going to do the whole thing again here, which includes everything. So hopefully we get everything right. If I don't, then I'll add annotations in the edit. But hopefully this helps some of you guys out. You have your exam in 2 or 3 days. I'm filming this on the Monday, so it's not long left to go, and hopefully it helps people in the future as well who might be doing this exam and want solutions. So without further ado, let's jump straight into things. Question 1, we have this rectangular sheet of cardboard, and we have some length and some heights, I assume. So that its length is twice its width. Its width is h, its length, that would be 2h here. And what we're doing is we're cutting out these little squares of side length x, and we're folding this up into a nice open box. And the volume is greater than 0. Of course, the volume can't be equal to 0. And part A asks us to show that the volume of the box can be expressed in this form. Okay, so that shouldn't be too tricky to do. First of all, let's figure out what the length is. The length is twice its width, so the length is the bottom here. The length is 2h, and then we subtract off 2x from both sides. So 2h minus 2 times x, but we're given h is equal to 25, so that's going to be 50 minus 2x. And what's going to be the width? The width is just going to be, well, in this picture, the height. Actually, let's just call it the width. So it's going to be this h distance here, and then we subtract off 2x from both sides. So in this case, it's just going to be h minus 2x, but that's just going to be equal to 25 minus 2x. And what is the height? Well, the height is just going to be, we fold it up, so it's just going to be x. I don't like how they used h here for the whole distance of the width here. Maybe we should call it another variable. Let's just call it I don't know, t for tallness or something. I really don't know, but the tallness of the box is equal to x. So the volume, if you combine all these equations together, the volume is the length times the width times the tallness. That sounds so weird. And if you combine everything together, that's just going to be 50 minus 2x, and we have 25 minus 2x, and then times an x. But you may notice it's not quite in this form yet. What's different? We don't have a 50 to start off with, and you can kind of see why. We can turn this factor into this factor over here if we factor out a 2. Right, so if we factor out a 2, it's going to turn into 25 minus x. So let's rearrange this a little bit. That's just going to be, let's put the x at the front. So we have x, we factor out a 2. Let's put this factor next here. So that's going to be 25 minus 2x. And then we'll put whatever remains from this factor. So that's going to be 25 minus x. And then we are done. Well, not quite done with the question, but done with that part. State the domain of the volume of the box. Okay, so before we continue, because we have an expression for the volume, we might as well define this on our CAS. So let's jump to our CAS, and what we'll do is we'll define v of x to be equal to, we have 2x, and be careful, don't put a bracket straight away, put multiplication, otherwise the CAS will think this is a function when it's not. So we have 25 minus 2x, and then times 25 minus x. So we define our function. And now we want to take a look at the domain of this. It would be nice if we can graph this probably. So let's put in v of x and see what that gives us. That is not very useful at all. Maybe we have to adjust the domain because, if we take a look at this picture here, let's go back to the whiteboard. What are the possible values for x? Well, first of all, these squares can't really overlap here. Otherwise, you can't really form this box. So the h here, that's going to be 25. So the biggest x can be is 25 over 2, because once x gets to 25 on 2, you're going to get something that looks like this, where these edges are kind of like right against each other, and that's going to be the maximum that x can be. So I'm assuming this would be x on the interval. It can't be negative because x is a length, and it can go up to 25 on 2. let's verify that on CAS. So looking for when this volume here is positive. So this is extremely unscaled, but you can kind of see this should be a cubic and it comes back down right over here. I want to see if I can modify this a little bit. So let's go to Windows Zoom and we're going to go to Windows settings. X min, that's set to 0. X max, that's to 25 and 2. And Y, that's, let's say it also works. That doesn't work. And yeah, that is ridiculous. So let's adjust that again. Let's go to Windows settings. X min 0, X max 25 and 2. Y min is 0. Let's go for something equals like 1,000. Hopefully, it's going better. Windows Zoom, Windows settings, 0,000. Let's go for 1,500. That should be sufficient. So it's sufficient. Come on. Windows Zoom, Windows settings. Let's go for 2,000. I'm maybe even 2.5k. And what is happening? Why is it not doing anything? Windows settings. Let's go for 5,000. There we go. So we get a shape that looks like this. And as you can see, this is when the volume is positive. Okay, cool. So that should be that question. I made a horrible mistake. We don't want to have inclusive endpoints here because the volume is greater than 0. So if you include those endpoints, your volume has the potential to be 0. Next, find the derivative of the box. And yeah, as you can see down here, we want to find the maximum possible value. So let's use the analyze program on the CAS. This is a program you can get if you go to my websites, but if you don't have the program, you can just differentiate this using the usual method. So let's go to analyze. We'll put in our v of x here, comma x, and we know our domain. So let's add a domain. So 1, lower bound is 0, upper bound is 25 and 2, and we get a whole lot of outputs here. And we can see, let's approximate by pressing Control Enter instead. And domain 0 and 25 and 2. And we get some output. So we have a stationary point, which is local maximum right over here. So if you take a look at the derivative is right over here. To get the derivative, if you don't have the program, you can just do shift minus x and then v of x. That's a nice shortcut. There's a derivative. It's going to be 12x squared. So 12x squared and then minus 300x. And then we have plus 1250. And we have to calculate the maximum possible value of the box and the value of x for which this occurs. So let's call this v box prime of x. And what we want to do to show you some working out is we let v box prime of x be equal to 0. And if we solve this on our CAS, that's going to give us x is equal to well, we kind of solved it using the analyze program. We get x equals 5.28 because that's the stationary point. But if you want, you can solve this manually. So you can solve this guy here equal to 0 with respect to x. And you get a few values. I'm assuming this one's going to be the negative solution, which we don't want because it's not the negative solution. Maybe I'm wrong. But this value up over here, that's 19. So that could potentially be a stationary point. However, this is outside of our domain because remember, we only go up to 25 and 2, which is only 12.5. So we kind of reject this upper solution here, which means we're going to go for 5.28. And find the maximum possible value in the value of x. I'm assuming we want exact values, so let's go for that because it's not saying approximate or anything. So x is equal to, that's going to be negative 25 root 3 minus 3 divided by 6. So that's going to be the x value for the stationary points. And now we just got to sub this back in. So v box of that particular value, so negative 25 root 3 minus 3 divided by 6. And that's going to give us, you just need to sub it back into the function, which isn't too bad to do. So you can have v of this guy over here. Let's take this and put it into there. And we get 15,625 root 3 on 9. 15,625 root 3 over 9. And let's just approximate this. That's 3007. That's what we got from the analyze program as well. That's the local maximum. Right. Okay, we don't have to check endpoints because at the endpoints then the volume is 0. So this has to be the maximum. Okay, waste minimization is a goal when making cardboard boxes. Percentage waste is based on the area of the sheet of the cardboard that is cut out before the box is made. And we want to find the percentage of the sheet of cardboard that is wasted when x is equal to 5. Okay, so how much is wasted? So the waste over here is equal to 4 times x squared. Hopefully that's clear why, because you waste these little squares that you cut out. So that's the waste. And we want to find this as a percentage of the sheet of cardboard. So what do we want? We want h over h times 2h, because that's the area. So we have area is equal to h times 2h, but that's equal to 25 times 50, which is something. What's 25 times 50? 25 times 50 is 1250. So the percentage waste, you can write this as a function of x if you want. That's simply going to be 4 times x squared divided by 1250 times 100. Right, so at x is equal to 5 is what we want. Oops. I realize part of the CAS on my recording software is covering. So at x is equal to 5, what do we have? We have, well, let's just plug it into the CAS. So we want 4 times x squared divided by 1250 times 100 such that x equals 5, and we get 8. So it looks like this is going to be 8%. That's the percentage of the sheet of cardboard that is wasted when x is equal to 5. Okay, that's part E. Let's take a look at part F. So now consider a box made from a rectangular sheet of cardboard where h is greater than 0 and the box's length is still twice its width. So now we choose any arbitrary h, or not arbitrary, but some h value greater than 0, but the relationship between length and width is still the same. We're going to let VBox be the function that gives the volume of the box. State the domain of VBox in terms of h. Okay, so now what we're doing is we're rewriting all of this, but kind of in terms of h as well. Okay, so first of all, it would be nice if we can find an expression for the volume. We don't really need that, by the way. So first of all, what we can do is we can notice that x has to be greater than 0. So we have 0 greater than x, but x has to be less than some value. And in particular, it can't go past h on 2. Because it goes past h on 2, then these squares overlap, and that's no good. So we want x to be less than h on 2. Let's do that. And hopefully that's right. Now we want to find the maximum volume of such a rectangular box in terms of h. It's kind of similar to the one before, but now we do it for any arbitrary h. So let's define the volume. So now let's call it a v. Yeah, we'll just redefine v box of x over here. That's going to be, well, how do we get the volume? It's going to be 2h minus 2x, that's the length. And then we have h minus 2x, which is the width here. And then we have to multiply by x, which is the height. So what do we have? We have 2 times h minus 2 times x, then h minus 2 times x, and then x. That's going to be the volume, and then we just maximize this like before. So let's see if we can do this on the CAS. Let's switch this over here so you guys get a better view of the CAS. So let's define, let's call it v2 of x. Now it's going to be equal to, we have x times, we did 2 times h minus 2 times x, and then we have h minus 2x, and then we have x like so that's v2. Now I could use the analyze program again, but because we have these parameters on the inside, probably not a good idea to use because it depends on what values of h we have. So let's do this the usual way. So we have shift minus and then x, and then we have a v2 of x. That's the derivative, and then let's solve this derivative here equals to 0 with respect to x, and we get two solutions. Which one is, so which one should we take? We want x to be less than h on 2, so let's add that restriction. So we have x such that 0 is less than x is less than h on 2, and we get so this is the solution we're after here. So on our whiteboard, let's go back to this view here, and what do we have? We have a v box, and if you want, you could probably write the derivative as well. It's probably a good thing to do. What is the derivative, by the way? It's equal to, it was something up here. There we go. So it was equal to, we have 12x squared, and then minus 12hx plus 2 times h squared. And if you solve a v box prime of x equals to 0 for suitable values of h, then what you're going to get is x is equal to the values we found below, which was that value. So we have negative. We could probably bring that negative into those parentheses and switch the two numbers around, so we have 3 minus root 3 instead. And this is divided by 6 still. And now we just have to find the maximum volume by subbing this back in. So we have a v box of that value, so h 3 minus root 3 on 6. And what's that going to be? So let's do v2, and we're just going to sub in this value over here. So let's copy that in, and then we get h cubed root 3 on 9. So this is h cubed root 3 on 9. There we go. I wonder if the analyze program can handle this. So let's go to analyze, and then we'll go to v2 of x, and then comma x, and we want a domain. Let's go from 0 to h on 2. And what do we get? So it looks like we get this negative here. Maybe the CAS doesn't understand that h has to be positive, even though I did put that in. Yeah, maybe something to be careful of if you have the analyze program and you want to use it. Probably not good to use it if you have undefined parameters in your function. But yeah, we do get this local maximum here, as we expect. Okay, so question G, now consider a box made from a square sheet of cardboard with side lengths of h centimeters. Show that the maximum volume of the box occurs when x equals h on 6. Okay, a box from a square sheet of cardboard. So what do we have? We have a square sheet of cardboard. There's our cardboard. Here's h, and we cut out these squares just like before. So let's try to find the volume. So v, let's call it v square of x. That's going to be equal to h times, or h minus 2 times x. Now this is squared because it's the same, yeah, it's a square. And then we multiply it by x because that's going to be the height. So let's define that on our CAS. So let's call it v square. So define v square of x is equal to h minus 2x, but we square it, and then we have times x. And what is going on? Why did I put a multiplication there? And I spelled define wrong. So define this guy. And what do we want to do? We want to maximize. So just like before, let's solve the derivative with respect to x of v square of x is equal to 0 with respect to x. And we got two solutions, but of course we want 0 is less than x is less than h on 2. And hopefully it's clear why it's h on 2. And we get h on 6. So let's write that down. So v square prime of x is equal to, I didn't even get the derivative, so let's do that. So what's the derivative of v square of x? It's 2x minus h, 6x minus h. So yeah, 2x minus h, and then 6x minus h. And solving this equal to 0, so let v square prime of x equal to 0. And what does that give us? It gives us x is equal to h on 6. Yeah, when h is greater than 0. Okay, so that should be it there for question 1. Let's take a look at question 2 now. So what do we have? It looks like Riemann sums. So 4 rectangles of equal width are drawn, and the approximate area under y equals x squared from 0 to 1. So here it is, Riemann sums. The heights of the rectangles are the values of y equals x squared, so that we're using the right endpoints here. State the width of each of the rectangles shown above. So we have an interval from 0 to 1, so the length of the interval is 1. We're dividing up into 4 equal parts, so the width has to be equal to a quarter. Find the total area of the 4 rectangles shown above. So not too tricky to do. Let's go into the CAS. A nice thing to do when you're starting a new question is just to go to doc inserts and go to a problem, just so you get a fresh new page, and if you press bar, there's no variables defined. So we're just going to define, let's just call it f of x because why not, equals x squared. And we want to find the total area of the 4 rectangles shown above. So the way you do that is you take the width of each of the rectangles, so that's a quarter, and then he times by the sum of the heights of each of the rectangles. So how does that work there? Well, you have f of a quarter, that's the first rectangle, and then you have f of a half, which is the next rectangle, then f of 3/4, and then f of 1, which is the final one, and that's going to be 15 on 32. So it's just 1 mark, so you don't have to really write down working out. If you want, there's the Riemann sums program. So if you go down to methods integral calculus, there's Riemann sums, and you can just type in x squared, comma x, and then you go from 0 to 1. And number of partitions is 4. We're using the right endpoints rule, and it gives you the approximated area right away with the actual area, if that's any use. But yeah, 15 over 32. Find the area between y equals x squared, the x-axis, and line x equals 1. So that's just going to be the integral from 0 to 1 of x squared. Don't really know what that's 2 marks, but I guess we have to write down a bit of working out. So that's the integral from 0 to 1 of x squared dx, and that's going to be equal to, well, the program already gives us to it, it's a third, which is nice. So this is 1/3 here, and yeah, I mean, if you want, you can go to integral from 0 to 1 of x squared dx. That's literally what the program does anyways. It just computes that integral, so nothing too fancy going on. So yeah, that should be it. Let's take a look at the next question, which is, it's on the next page. So we have part D now. The graph of f is shown above, or below rather. Approximates integral from -2 to 2 using 4 rectangles of equal width and the right endpoints of each rectangle. So we're not even given the function, the rule of the function, so we have to kind of eyeball it. So -2 to 2. So we're starting here, and we're ending here, using 4 rectangles of equal width, so we can fit 4 rectangles of width 1 on this interval, and the right endpoints. So if you take a look at the right endpoint, that's going to be right over here for the first rectangle, and then for the next rectangle, it's going to be over here. That's the right endpoint, and then for the next rectangle, it's going to be right down over here. That's the next rectangle, and for the next rectangle, it's going to be over here. So you want these areas. Just be very careful. These areas are positive, and these areas are negative because it's below. So we just count the squares, I guess. You just need to make sure you read the scale properly, because each of these squares or these rectangles have an area of 2, because the y-axis goes up by increments of 2. So we have 1, 2, 3, 4, and then now we subtract off all these squares here. So this was 1, 2, 3, 4, then 5, 6, no, 1, 2, 3, 4, then 3, 2, 1, 0, and then -1. Right, you can count the squares however you want, but you have to make sure you subtract off these. So we get a -1 squares, but each square has an area of 2. So this is going to be -2. Hopefully that's right, and I didn't make any counting mistakes, otherwise that would be a little embarrassing. So parts of the graph x squared and root x are shown below. Find the area of the shaded region. Again, that's not too tricky to do. On the CAS, what you can do is, let's just use this that we already have. Just got to subtract off square root of x, and it gives us that's not right. X squared, no, square root of x comes first. What am I doing? Because square root of x is the one at the above, but we're just off by a negative sign anyways. So it's the big function minus the small function that we see, and we get a third as well. So I guess we just go for a third here, just 1 mark. Okay, so part F, what do we have? We have y equals x squared transformed to y equals ax squared. So we have some dilation. We want to find the values of a such that the area of some region is equal to a third. So we'll figure out what that region is in a sec. Give your answer to 2 decimal places. So find the values of a for which some region is equal to the third. So first of all, let's try to figure out what that region even is. So maybe we can probably graph this out on the CAS just to see what on earth is going on here. So we have insert a graphs page, and we'll type in a times x squared, And let's create a slider, and then we'll press tab, and then we'll type in square root of x. So we have something like this. So a is on the interval 0 to 2, so let's change these bounds here. So this is going to go from 0, and we want to go to 2. And let's take a look at what the region is. So the region is root x between ax squared and root x, and the lines x equals 0 and x equals a. So x equals a is somewhere. Let's see if we can get that on the CAS. X equals a is a relation, so it's a graph that we have to go to graph entry edit, and you want to put in relation. So let's type in x equals a, and there it is right over there. Let's see if we can zoom in a little bit so we can get a better view. So window zoom, let's go to window settings. We're only operating on the interval 0 to 2 because that's the values of a. Y min is, let's go for 0, and then we'll go up to, now let's just do 4. Okay, so we have something like this going on. Let's change the sliders a little bit. So if we, now let's change this to 0 first of all. That's wrong. So we have, okay, if we scroll our a little bit, let's change the window settings again. I think I zoomed in a bit too much, so we'll go to window zoom, and then we'll go window settings, and x min, let's go for -1, let's go up to 3 instead, and y min, let's go for -1 up to let's say 5. Okay, that should be a bit better. So we can kind of see there's two regions bounded by the two graphs, and the line x equals 0 and x equals a. There's this little kind of oval region and this little triangle region as well. What happens for different values of a? So it looks like when a is equal to 1, let's try to get a equals 1. So when a is equal to 1, we should just get one region, I believe. But we could also have two regions. It looks like it's when a is greater than 1. So when a is less than 1, we have that one region, because we're only going between 0 and a. And when a is greater than 1, it seems like we have two regions which we need to deal with. And both of these regions, or both of these cases, could potentially have an area of a third. So let's try to do that. So let's take a look at the case when a is less than 1. And let's see if we can get anything happening there. So when a is less than 1, what's going to happen? Let's switch back to the small view for the CAS. So a is less than 1. What do we have? We have the integral, so area, is equal to the integral from 0 to a of big minus small. Now big minus small in this case is going to be root x minus ax squared. So we have root x and then minus a times x squared and dx. And all we have to do is set this equal to 1/3 and then solve for a. Okay, so what happens if a is greater than 1? Well, as you can see on our CAS, we get two regions. So let's make a greater than 1. We get two regions over here. We get this little oval, and then we get this triangle. So we have to split this up across the intersection points. So let's find the intersection points. To find the intersection point, again, not too tricky, you can just do this on the CAS. We can just solve x squared, or a times x squared rather, is equal to square root of x, but here's a bit of a problem because a is defined. We don't really want that. Yeah, because a is defined already. Let's delete a for now, and we'll put it back in later for the graph. So let's solve this. We get a bit of a mess, but maybe if we include the restriction that a has to be positive, so 0 is less than a, is less than or equal to 2, then we get this. This makes sense because x equals 0 is definitely an intersection point. If you take a look at the graph, I think it's broken now, but yeah, whatever. They intersect at 0, and you get this other intersection point as well. So a to the -2/3, it seems to be. So we have to split this up across that intersection point. So the area is equal to the integral. Let's put a back to something. Let's put a equals 1.5 for instance. Hopefully that works. Maybe the CAS is just broken. Let's see. Let's go to tab. Oh dear. tab. I want to put in my functions again, so let's go to entry edit, let's go to function, and well, can we scroll up? Create a slider. There we go. So it's a big mess now, but let's make A slightly bigger, and yeah, we get 2 regions, so we have to split it up across the intersection points. So if we take a look at the integral from 0 to a to the negative 2/3, big minus small is a root x minus a times x squared dx, and then we also got to add the integral from a to the negative 2/3 all the way up to a of the other way around because the functions switch. So ax squared minus root x dx, and we want to solve this equal to 1/3. Okay, so let's solve both of these on the CAS. Shouldn't be too tricky to do, we just have to type in a bunch of things. So yeah, let's delete a once again because a is being defined at the moment. So we're going to solve the integral from 0 all the way up to a of root x minus a times x squared dx is equal to 1/3, but we have to have the restriction that a is between 0 and 1. It's missing a comma x, so we got something. You have to solve for a, not x. What am I doing? So if we do that, we get a equals 0.77 if you approximate. So a equals 0.77. How many decimal places do we want? 2 decimal places, so let's go for 77. Or let's see if we can get a solution for the second case when a is greater than 1. So let's recycle this a little bit. Now we're going to go from 0 to a to the negative 2/3. We take this guy, and then we're going to add the integral. So shift plus the integral from a to the negative 2/3 of a times x squared minus the square root of x, and we're going to go up to a, and everything should still be the same. So this is a dx here, and we solve this equal to 1/3, and now a has to be between 1 and 2 instead, and it approximates 1.13, it seems to be. So let's go for that, or a equals 1.13. Hopefully that's right. I'm quite sure there were supposed to be 2 solutions anyways. So yeah, that's question 2. Let's take a look at question 3 now. So we have a function, this q function, it's difference of 2 long. So let's define that on our CAS first of all. We're going to define a q of x to be equal to, we have the logarithm of x squared minus 1, and then minus the log of 1 minus x. And to get the maximum domain, just type in domain of q of x with respect to x, negative infinity to negative 1. So domain is negative infinity to negative 1. And to find the range, well, that's not really a good way to find the range on the CAS. Best thing you could probably do is sketch it. So let's go doc44, and we're going to sketch q of x. And let's see what we get. It looks like it's just one side of the log that goes from negative infinity up to infinity. So we're just going to take the range to be the real numbers. So range is R. Find the equation of the tangent to the graph of q when x is equal to negative 2. That's nice and straightforward to do. We just need to do the tangents command. So that's menu 4, 5, which is not the correct one. It's menu 4, 9. I forget my commands. So we put in q of x, comma negative 2. Is that what we want? Yes. Equation and tangent to the graph of q when x equals negative 2. Let's press enter, and we get negative x, negative 2. And equation, so we kind of want y equals something there. Find the equation of the line that is perpendicular to the graph of q when x is equal to negative 2 and passes through the point negative 2, 0. Let's see, find the equation of the line that is perpendicular to the graph of q when x is equal to negative 2 and passes through the... I don't know why they have to put so much stuff in there. This is just a normal line question. So we have menu, calculus, then we have normal line. and let's just put in q of x, comma x, and then comma -2, and x plus 2 should be the answer. And y equals x plus 2 definitely passes through -2, 0. Okay, let p of x equals to this function, so that's defined. So we define p of x to be equal to, we have e to the -2x and then minus 2 e, I have to do at e on my keyboard, to the -x, and then we have plus 1. And we want to explain why p is not a one-to-one function. Let's take a look at p. So we tab, and then we have, oops, p of x here, and let's see what that looks like. So it looks like, yeah, this is definitely not one-to-one because we have this little dip over here, this local minimum. So we have a specific y value, which has 2 possible x values. So what we can say is p has turning points at 0, 0, hence not one-to-one. Or hence, you should probably say hence doesn't pass the horizontal line test. Oops, it doesn't pass the horizontal line test. And because of that, it is not one-to-one. Find the gradient of the tangent of the graph of p at x equals a. Find the gradient. So this is just taking the derivative and evaluating at a. So we can do shift minus derivative of p of x such that x is equal to a. And we get this expression here. So that's going to be 2 e to the -a. And then we have minus 2 e to the -2a. That should be it. Okay, so that's part D. Let's take a look at part E. Okay, so we have a diagram that shows the graph of P. So here it is, and the line y equals x plus 2. The line y equals x plus 2 and the tangent to the graph of P at x equals a intersects with an acute angle of theta between them. So we have the line of y equals x plus 2, here it is, and the tangent to the graph of P at some a value intersects with an acute angle of theta between them. And we want to find the angles, or we want to find the values of a for which theta is equal to 60 degrees. Okay, so what we can do is the following. We're just going to consider some points a. So let's say, let's pick a value of a. Let's say this one over here, okay? And we're going to try to construct the tangent to it. And what we're going to do is we're going to try to compute its angle with the positive x-axis. And all we're going to do is subtract that from, maybe there's a better way to do this. Actually, what we can do is we can say we want some line which has an angle of 60 degrees with this, with the x plus 2 line. So this is 60 degrees, or pi and 3 radians. And then we want to try to find the gradients of this particular red line. Then what we can do is look at our graph of p of x and figure out where a gradient of whatever gradients that is would occur. So it sounds like a lot, but it's not too bad. There's actually 2 possible ways you can get an angle of theta equals 60. Because you could have one going maybe like this, that's roughly 60, and maybe another one like this. So there's 2 possible 60-degree angles. So for the first one, looks like there's only one possible way to do that. For the second one, looks like there might be 2. I'm not too sure, because there could be one here, or there could be one here, but we'll have to check with both of them. So let's try to find the gradients. So how do we find the gradients? First of all, this is a 45-degree line of pi and 4 radians. What happens if you take pi and 4 and add pi and 3? So we're trying to find a line that's 60 degrees to the x plus 2 line. So we take pi and 4, let's add on pi and 3, and let's see what we get. So pi on 4, and then plus pi on 3. That's going to be 7 pi and 12. And to find the gradient, all you need to do is take the tangent of that. So we have the tangent of this guy is not that value right over there. So that's kind of like the gradients we're after on this p of x curve. So let's try to do that. What we're going to do is we're going to take the derivative. I'll show you guys two ways of doing this. You take the derivative of p of x at some points a, which we've actually already done. We've already done it over here. So all we need to do is solve this derivative at some points a equals to this gradient we just found with respect to a. And can we get, yep. So we get some a value. This is approximate, so we can get, we don't have to use exact values. So we have a specific value of a. Now, how about if we try pi and 4 minus pi and 3? So there's the angle. Let's take the tangent of that angle. There it is. And then we're going to do a similar solve. So we're going to try to solve a gradient, which was all the way up over here, equals to this particular value with respect to a. And we get another value. Okay, so we have two a values. We have this a value. I don't want to do that. We have this a value, and we also have this a value which we found earlier, or actually we just found that a value. So here's the values of a, and that really should be it. I think that should be the answer, hopefully. So how do we write this out with a bit of working? So we have the angle of lines. This will be pi on 4, and then plus or minus pi on 3. Now, what's the gradients going to be? So gradient of these lines is going to be the tangent of pi on 4 plus or minus pi on 3. And what is that going to be? That's going to be equal to, well, I think we found it was something, so minus, what was it? It was root 3 minus 2. Or, and what was the other one? It was something, negative root 3 or something. I'm not too sure. Negative root 3, negative 2. So negative root 3, negative 2. And what we do is we just solve equal to those values. So we solve p prime of a is equal to root 3 on 2. And that gave us some value for a. And we also solve p prime of a is equal to negative root 3 minus 2. And that gave us some value for a as well. Let's see which one's which. So for this one, the root 3 minus 2, that's the negative 0.11. Negative 0.11. And for the root 3, that should be the other one, so negative 0.67. And that should be it. Okay, part F, find the x-coordinate of the point of intersection between the line y equals x plus 2 and the graph of p, and hence find the area bounded. So what is this asking? Find the x-coordinate of the point of intersection between our 45-degree line, so the x plus 2, and the graph of p. So after the intersection points, first of all, right over here, that shouldn't be too tricky to do. What you can do is solve x plus 2 is equal to p of x with respect to x, and yeah, we get, is this approximate? Both correct to 3 decimal places. So we have negative 0.750. Oops. Sorry. Intersection point is negative 0.750, comma, and we just have to sub that x value back into, let's say, p of x. So p of x, such that this value, and that gives us something, 1.24. I think my calculator setting's a bit wonky, so 1.249 or 1.250. Actually, this is just the x-coordinate, so nah, we don't need that value. I was reading this wrong, so it should be negative 0.750. This is the something to do with the intersection, so there it is there. And hence find the area bounded by y equals x plus 2 in the graph of p, and the x-axis both correct to 3 decimal places. So what is that area they're talking about? It's the area bounded by x plus 2, here's x plus 2, p, and the x-axis. So it's just that little triangle bit over there. So this little area. So that's not too tricky to find. So all you need to do is split up the integral, because you integrate across kind of two functions. So the area is going to be equal to the integral. I'm going to go from negative 2 to negative 0.750. now, first of all, we have x plus 2 dx, and then we add the integral from negative 0.750, and we go all the way up to 0 because that's the x-intercept, which we kind of mentioned earlier, and we do this on p of x dx, and we just need to evaluate this on the cos. Shouldn't be too tricky to do. So let's see what that gives us, and we have the integral from negative 2 to, well, let's just take, negative 0.75 of x plus 2 dx, and we're going to add the integral, so shift plus, from negative 0.75 all the way up to 0 of p of x dx, and that gives us, let's approximate, 1.038. 3 decimal places, so 1.038 should be the answer. Okay, so that should be all of question 3, I believe. Now we are on to question 4. I remember this being a fairly tough one when I saw it for the first time, so let's see if we can do it again. A teacher coaches their school. The speed is normally distributed, so W, this represents speed here. It's normally distributed, so speed. The teacher sets the ball machine with a mean speed of 10 and a standard deviation of 0.8. So W is normal, so what we can say, let's write it over here. So W, this is normally distributed with a mean speed of 10, standard deviation of 0.8, and squared because of the notation. Determine probability W greater than or equal to 11. So let's go into our CAS. Let's open up a new problem. So insert a new problem and calculator, and we're going to go to menu, 5, I think it was 2 for CDF. Lower bounds is 11, is it? It's greater than 11, so lower bound, and then upper bound is infinity. The mean is 10, and we have 0.8. So that's going to be 0.10 something I saw, so 0.1056. 3 decimal places, so we'll just go for 106 there. Find the value of k in meters per second, for which 80% of the ball speed are below. Okay, so we have our normal curve over here, and we want to find the value of k such that 80% of the ball speeds are below. So we have 80% of the ball speeds, which is a pretty big chunk, and we're trying to find that specific value of k for which we have that specific probability. So this is inverse normal because we're trying to find a value on the x-axis. So to do inverse normal, we're going to go to menu, 5, and then 3 for inverse normal. The area in this case is 0.8. If this area is on the right hand side, you have to take the complements because the CAS only thinks that the area is on the left hand side. In this case we're fine, so we can just put in 0.8. Mean was 10, and then we had 0.8. Was it 0.8? Yes, it was 0.8. So we have 10.67. So we have 10.67 meters per second. This is 1 decimal place, by the way. I still make this mistake to this day. 10.7, there we go. The teacher adjusts the height setting of the ball machine. The machine now shoots balls high above the tennis table. Unfortunately, with the new height setting, 8% of the balls, so we have some proportion here, do not land on the table. Let p hat be the random variable representing the proportions of balls that do not land on the table in random samples of 25 balls. And we want to find the mean and the standard deviation of p. Okay, so how do we do that? The mean, let's use E of p hat. That's just going to be p, but that's just 0.08. So this value, the standard deviation of p, so SD of p, that's going to be equal to square root of p, 1 minus p, divided by n, which isn't too tricky to calculate. That's just 0.08 times 0.92 divided by 25, and then we put a big square roots over it, and we calculate this on the CAS. So we have the square root of, let's do something over 25, 0.08 times 0.92. That gives us 0.054. 0.0. This is correct to how many decimal places? Doesn't say, so I'm assuming this is exact. So let's go for root 46 on, was that 125 I saw? Yes, 125. So square root of 46 on 125 should hopefully be the answer. Okay. Part D, use the binomial distribution to find the probability that p hat is greater than or equal to 0.1. So we have proportions, we're using the binomial approximation, so we have to convert this guy over to a binomial random variable. So we let x be binomial, number of trials is 25, and the probability of success, oh, that's just the population proportion, which is 0.08. So we convert this over to x, which is the probability. You just multiply everything through by the sample size. So x now is greater than, what's 0.1 times 25? It should be 2.5, I believe. So greater than 2.5. But this is the same as the probability that x, because it's discrete, so you can't really have fractions. Well, you can, but it's binomial, so it's only on the integers. So x is greater than or equal to 3. So this is binomial, nice and simple to do on the CAS. So we go to menu, 5, and I think it was B for CDF. So CDF, because we have an inequality, so we have 25, 0. Was it 8 or 0.8? It was 0.8. And the lower bound, we go from 3 up to 25. That gives us 0.323. And how many places is this? This is 3 decimal places. So 323 should be our answer. So equals 0.323. Okay. So that's part D. Let's take a look at the rest of it. So now the teacher also adjusts the spin setting on the ball machine. The spin is measured in revolutions per second. It's continuous. We want to find the maximum possible spin applied by the ball machine in revolutions per second. Let's see. That should be 50, because that's the largest possible value of x. So x is representing spin here. So x only goes up to 50. Now we want to find the median spin in revolutions per second. I guess the nice thing we could do on the CAS is just define the piecewise function. I'm usually against defining piecewise functions on the CAS because it's fairly annoying to do, but in this case I think it's probably worth doing. So let's go for, oh, where's the piecewise? So you can go to the templates button, and we can go to the piecewise, which is right over here, I believe, and let's type in the piecewise functions. So it's going to be x on 500 when x is between 0 and 20, so 0 less than or equal to x less than or equal to 20, and actually just less than 20, and it's going to be something else, so that's going to be 50 minus x, and then we divide by 750, and this happens when x is between 20 and 50, so 20 less than or equal to x less than or equal to 50, that's our piecewise function, and we want to find the median spin, which is simply just integrating or solving the integral. So let's do a solve here. We're going to solve the integral that goes from 0, because that's kind of like the start of the domain, so 0 up to some m of f of x. I didn't even define that function, silly me. We should probably define f of x to be equal to exactly this guy here, and now we can do the solve integral. So we have solve integral from 0, because that's kind of like the start, so 0 all the way up to some m of our function f of x dx equals 0.5, and we solved it with respect to m, and that should give us the median. Can we approximate this? Yeah, usually if you get some weird output, if you just approximate it, then it works fine. So 22.61. How many decimal places is this? This is 1 decimal place, so 22.6 should be the answer. So we integrate from 0 to m of f of x dx is equal to 0.5, and that gives us m is equal to 22.6, was it? Yes, 22.6. Find the standard deviation of the spin in revolutions per second. Correct to 1 decimal place. Okay, so standard deviation of x That's just the square root of the variance of x. How do you find the variance of x? You have to find the expectation of x squared and minus the expectation of x, but then you square the whole thing. So what's the expectation of x squared? The expectation of x squared is the integral from 0 to 50, because that's the domain where it's non-zero, of x squared times f of x dx. And we can solve this on the CAS pretty easily. You just need to do the integral of from 0 to 50 of x squared times f of x dx, and that's approximates, that's 650. So we have 650 over here. And then we also have to minus the expectation of x squared. Let's calculate the expectation of x. What is that? That's just going to be basically the same thing, but we, instead of squaring, we just take x and then we multiply. So once again, approximate, that's 23.3333. So 23.33, so on. So therefore, if we put everything back into the formula, SD of x, that's going to be equal to the square root of 650 minus 23.33 ... squared in a square root. Let's calculate that on the CAS. So we have the square root of 650 minus this guy, but then we square it, and that gives us 10.274. Actually, this is one decimal place, so that really should be 10.3 instead. Easy mistake to make. So that is that, and here comes the big question. I remember this one. So now what do we have? Teach adjust the spin setting so that the median spin becomes 30 revolutions per second. This will transform the original probability density to a new density G, which has this form. Find the values of A and B for which the new median spin is 30 revolutions per second. Okay. So what do we want to do? We know the original interval was from 0 up to 50, right? That's where our probability density function was defined, and it's non-zero. And now we're kind of stretching this out. Where was the original median? The original median was 22.6, so like almost in the middle. It's a bit less than halfway. So it was 22.6 right over here. So here's m equals 22.6. And what do we want to do with this? We want to kind of scale this up so that we have some new scale. So it still goes from 0, because if he dilates 0, it still stays at 0. We want this to move all the way up to 30. So if he dilates the x-axis, then the density will also dilate with it. Right, so what's the dilation that would get us from 22.6 to 30? So m is equal to 30 now. Well, that's just the ratio. You just take 30, you divide by 22.6. Let's see what that gives us. So 30 divided by 22.6 gives us 1.32. So 1.32, do we need 3 decimal places? 2 decimal places, so 1.327. Let's go for 1.33. 1.33, this would be the dilation from the y-axis that we need to have to move the median from 22.6 to 30. So 1.33, that's going to be what's going to be applied to everything to scale it. So how is dilation from the y-axis represented? Well, it's going to be this b here, right? So if the value of b in this expression is simply the dilation, so therefore we can conclude that b equals 1.33. Now, big problem if we do this. If we scale our density function, then the area will not be preserved, because we always want the area under the density to be exactly 1. If we dilate by 1.33, now the area actually becomes 1.33, which we don't want. That's why we have this a here to compensate for that. So we need to think of what dilation from the x-axis now will compensate for that to make sure the area is preserved at 1. And that's exactly a reciprocal. Because once he dilates out this density, the area underneath, it's not going to be 1 anymore. The area underneath is 1.33. The way you fix that is he dilates from the x-axis by some amount. So now the area underneath here stays at 1. And how much do you have to dilate by? Well, you want to get from 1.33 down to 1. So you have to dilate by 1 over 1.33. Right, it's basically taking this area and asking yourself, what do I have to multiply the area of 1.33 by to get down to the area of 1? It's exactly the reciprocal. So we have a equals 1 over 1.33, which is exactly, what's 1 divided by 1.33? It's 0.75, yeah, 1. So 0.75, because it's correct to 2 decimal places. So we basically got the answers. Yeah, let's just write it down again. A equals 0.75 or B equals 1.33. And that is it. So that is question 4. Alright, we got the final question. Let's get this wrapped up here. So what do we have? We have a function. It's the sum of two sinusoidal functions. So we have a sine of x over 2 and a cosine of 2x. And first thing we want to do is we want to state the period of f. So period is just the length of one cycle. And we can see that, let's say we start at 0, we go 2 pi, it's kind of above and then it goes below. So I want to say it's 4 pi is the period. And it can verify that because the period of the first part of the sine, and the period of that is 2 pi over n. N in this case is 1/2, so the period is 4 pi. The period of the second part, 2 pi over n is 2, so 2 pi divided by 2 is pi. So if you have the sum of two trig functions, the period is simply just the lowest common multiplier, or lowest common multiple of those two periods, which in this case is going to be 4 pi. Now we want to state the minimum value of f correct to 3 decimal places. Let's get this function f defined on our cas. So where's my cas? There it is. So we'll open up a new problem. So doc41, add a calculator page, and we're going to define f of x to be equal to, we have the sine of x on 2 and plus the cosine of 2x. And what we want to do is we want to find the minimum. Alright, so this is something you can do with the analyze program. I'll also show you how to do it without the program. Should be straightforward anyways. So let's analyze f of x with respect to x. We want 3 decimal places, so let's approximate this by pressing Ctrl Enter. We'll add a domain, so 1 for yes, and then we'll go from 2 pi to 4 pi, because we can kind of already see roughly where the minimum would occur. And this is the inflection point section. We want the stationary point section. I should probably switch stationary point and inflection point in the next update, just so, because usually we want to look at stationary points and you don't want to see all these inflection points. So we can see negative 1.72 is the minimum. So we'll go with that. So this is just simply stating, so don't need to work out. So we don't need to show working out. So negative 1.27, 2. So negative 1.7, 3 decimal places, so it's 2. And we can also do this without the program. So if we just simply solve the derivative with respect to x of f of x equals 0 with respect to x, and let's put a domain. So we have 2 pi, x, and 4 pi, and you just need to plug in these values so you can try to take f of x such that, and then you go up and you enter these values in. And let's approximate this because it's not working. And you just need to try to plug in these values here. So I guess you have to do a bit of trial and error, or maybe you can guess it's going to be the 7.9 and the 10 by looking at the picture. So we can take this guy, plug that in, and we get something ugly. Yeah, negative 1.72. Alright, so find the smallest value of h for which f of h minus x equals f of x. So first thoughts when seeing this, it's probably better to rewrite the left-hand side as f of negative x minus h, just so we can read off the transformations easily. So what we want to do is we want to reflect our function first. That's what this negative is doing. This is a reflection in the y-axis. And what is this h doing? This is a translation by h along the x-axis. So if you're not too sure where I got this equation from, all we did is factor out a negative from x minus h because we want the coefficient of x to be 1 if we write it in this form. So there's a 1 here, so we have to factor out a negative. So the first thing we should do is reflect in the y-axis. So you could take this function and you can imagine reflecting it in the y-axis. I'll draw this in red and you'll get something that maybe looks like this. I'm horrible at drawing this, but let's see. We have a curve here and then it goes up and to negative pi and it goes down and then yeah, something like this. So that's what happens if you reflect this part over, and then now you have to ask ourselves, so what's the smallest value of h for which f of h minus x equals f of x, which means what's the smallest positive translation we can apply to this section so that it comes back over here. And the answer should be 2 pi, because notice we have to take, I'll do this in another color, we have to take this point over here and move it right across there. We have to take this maximum and move it right across there. We have to take this point and move it right over here. And yeah, those are all distances of 2 pi. So hopefully that's clear. This is something you can also verify on the CAS as well. So yeah, we have h equals 2 pi, should be the smallest one. Of course, you can have, I believe 6 pi would work as well, and 10 pi and 14 pi, hopefully you see the pattern, but the smallest one is 2 pi. Let's verify that on the CAS just to make sure we're doing things correctly. So inserts the graph, so 4, 4. We'll type in f of x here, and we get some wiggly thing. And let's press tab, we'll type in f of h minus x, but we'll set h to 2 pi minus x. Let's see if the curve maps on, and yes, it does nicely. And you can check if you type in f of h minus x, and you add a slider for h. Let's add a slider, and let's set our lower bounds to 0 because h is a positive number, as it says, and we'll go up to 2 pi just to check if there's any potential values which are smaller. You see that when h is equal to 2 pi, I guess can't really get there for some reason, maybe because this is approximate. Let's go for 7. Yeah, it's somewhere in there, so you can probably get there. If you try to make h even slightly smaller, then you're never really going to map on exactly. So you can be pretty confident that 2 pi is the smallest value. Okay, consider the set of functions ga of x, where now instead of that 2, we replace it with a. So let's go ahead and define that on a CAS. So on the CAS, we will go ahead and define g of x. You don't have to put a comma x, just g of x is fine because you can have a as a parameter instead of a variable. So we have sine of x over a, and we have plus cosine of a times x. So that's our function, ga. State the value of a such that ga equals f for all x. So we have to see what value of a makes this function look like this function, and clearly the value is equal to 2. So that's pretty straightforward. So a is equal to 2. Find an antiderivative of ga in terms of a. This is just an antiderivative, so we don't have to worry about the plus c constant. To do that, we can just go shift plus, and we just integrate to g of x dx, and that should give us the answer of sine of ax divided by a. So let's write this as a fraction. Oops. So sine of ax divided by a, and we have minus a times the cosine of x over a. Okay, that's part E, well, part 1 at least. Now use a definite integral to show that the area bounded by GA and the x-axis over the intervals 0 to 2 pi a is equal above and below the x-axis. So to show, so we can refer to this picture, I guess, to show that the integral, so for the case a equals 2, this is 0 to 4 pi. So we'll look on this picture, 0 to 4 pi is precisely this interval, is precisely this section of the graph here. Maybe I have to move it slightly left, but it's precisely this section. Now to show that the area above and below, is that's what it's saying? To show that the area, we want to show that the area bounded above and below is equal. Okay, so if you have equal area above and below, that means the integral over the whole interval has to be equal to 0, because areas below the x-axis will have a negative sign, areas above will have a positive sign. So if you just do a definite integral across the whole interval, then it should be equal to 0. That shouldn't be too tricky to do, hopefully. This is use a definite integral to show that. So I'm assuming we have to integrate from 0 to 2 times a times pi of GA of x dx. And that's the integral from 0 to 2 times a times pi. So we have the sine of x divided by a, and then we have plus cosine of a times x dx. And we've already evaluated the antiderivative on the cas, so this is equal to, well, we have sine of a times x divided by a, and we have minus a times cosine of x over a. And we evaluate from 0 to 2 times pi times a. This is 3 marks. I'm assuming you have to do a bit tech free. So let's try to do this. What happens if you plug in 2 times pi times a into x? Then you're going to get sine of, well, that's going to be 2 times pi times a squared. So 2 pi a squared divided by a, minus, if you plug 2 pi a into the cosine, that's going to be a cosine. The a and the a down here will cancel, leaving you with cosine of 2 pi. So that's the top bound, or the upper bound. What happens if you plug in 0? So we have minus sine of, this is your 0, and then minus cosine of 0. Okay, cosine of 0 is precisely equal to 1. Cosine of 2 pi is precisely equal to 1. Now notice a is an integer. I forgot an a here. That should be there. Notice that a is an integer, a positive integer, I'm assuming. Yep, a is a positive integer. And notice here we have 2 times pi times positive integer. Sine of an integer multiple of 2 pi is always 0. So this part is 0. So what do we end up with over here? This is equal to, we have a negative a, then minus negative a, which equals 0. So therefore, same area above and below. So therefore, area above cancels with the area below. So therefore, or hence, I guess, they have the same bounded area. So the signed area is what makes it cancel. Hopefully that's clear there. Okay, let's take a look at F. So explain why the maximum of GA cannot be greater than 2 for all values of A, and why the minimum value of GA cannot be less than negative 2 for all values of A. Okay, so if you take a look at the function g of A, you will notice that it's a sine of something plus cosine of something. So first, let's note that down. We'll note that sine of, was it x on A? I believe it was. So sine of x on A is on the interval negative 1 to 1. And we have cosine of a times x is also on the interval negative 1 to 1. So when you add these two guys together, sine of x over a plus the cosine of a times x, it cannot exceed the interval negative 2 to 2. It has to be bounded between that interval. So hopefully that should be a sufficient explanation. So yeah, GA of x is equal to this guy. The range has to be a subset of negative 2 to 2. Finally, last question of the exam, find the greatest possible minimum value of GA. This is a bit of a funny question to read. The greatest possible minimum value. Yeah, so this was a bit of a confusing one when I first saw it. I kind of understood what greatest possible minimum value was. It's like you have all these functions which are controlled by a here. So let's do this type of picture. Maybe you have this family of curves, let's say. So these functions are all controlled by a, let's say. And the greatest possible minimum value. So you take a look at the minimum value for each of these curves here. So for the minimum, it's over here, then you have over here, and you have over here. Now, what's the greatest possible minimum value? Well, it's the blue one, right? Because the blue one, it's a minimum value, but it's the greatest out of all these possible minimum ones. So that's how you can interpret it. Best way to do this question, I think, is just by looking on the CAS and see what's going on. So let's go to the CAS and we'll graph the function g of a. Let's open up a new calculator page, or graphs page rather. and we'll type in g of x. We'll create a slider for a. Now a is positive, so let's start this lower bound at 0, and we'll go up to, let's say, a decent number like 20 or something, I don't know. So this is g of x, or ga of x, when a is equal to 1. Don't think we want 0 because it's positive. And if you slide it along, you'll see that it kind of wobbles a little bit. Right. Essentially what's happening is that you have this sine of x over a. The period of sine of x over a is 2 times pi times a. So if you imagine you're just let's do the whole, both negative and positive. So you have sine of x over a, which kind of looks something like this. And the period is 2 pi a, like so. And you have the plus cos of a times x, which is added on, which kind of wobbles up and down along that dotted line. That's essentially what's happening. And notice, as a gets bigger, the period of the green function, so the sine of x over a, will get stretched out, because if a is getting bigger, then 2 pi a is getting bigger as well. So it's going to get stretched out. On the other hand, the cosine of a times x, the period is 2 times pi divided by a. So the period of the cos graph, which is kind of wiggling around on the sine graph here, it's getting smaller and smaller. So in a way, the greater your a value is, it's more likely that the minimums, so here's the minimum of the green, here's the minimum of the blue, it's more likely that the minimum of both of those functions will coincide, giving you a really big minimum overall, if that makes any sense. So as a gets bigger, the minimum values of both parts of the g function, so the sine and the cosine, they'll tend to get closer, and because they get closer, they're going to build upon each other to give you a negative number that's bigger in magnitude. Now what you want is to find the greatest possible minimum value of g. What does that mean? Well, you have the minimum value, but we want to make that as great as possible, or in small of magnitude as possible. And the way you do that is by reducing a as much as you can. Because we've noticed that as a gets bigger, your cosine function is wiggling around so much over here, that's the minimum of the cosine's probably going to be very close to coinciding with the minimum of the sine function, which is kind of like the big wave here. But if you make a really small, then notice what happens here. If you make a really small, then what happens to the cos graph that's kind of wiggling around on the sine? The period gets big enough, so the minimums of both the functions are further apart. So what does that mean here? It means that your sine function, the period will be small enough. So here's the sine function. The period's going to be small enough. And it's also with the cosine function, still kind of wiggling around the sine function in a way. But the period of the cosine is going to get bigger instead of smaller if a increases. So if a increases, the period of cos gets smaller. If a decreases, the period of the cos increases. So in fact, your cosine graph's probably going to look something like this. So the distance between those two minimums are further separated, which means they won't build as much to give you a really big minimum. So it turns out, if you take a look at the graph here, let's notice as you increase a here, then you have some kind of big minimum and some kind of small minimum. If you take a look at the question before, it was bounded between -2 and 2. And we can probably graph that if we press tab. Can we do that? I want to let's graph -2. As you can see, so this is the minimum over here, the absolute minimum that the GA functions can reach. If you make a bigger, then you're probably going to get to that minimum. But if you make a1, then notice what happens. It never actually reaches -2. It's further away, because the minimums of both of the sine and cos are further away, so they won't build on each other as much. So looks like a equals 1 is when g of a attains the greatest possible minimum value. Don't know if that explanation was clear or unclear or confusing or whatsoever, but it happens at a equals 1, because a equals 1 is when the minimums of both the sine and the cos are far away enough so that the minimums don't coincide. So when you add them together, the overall minimum isn't that great. So a equals 1, we just have to find the minimum value for a equals 1. So we can do that on the calculator page. It's pretty simple to do. So we can just go to analyze here. So analyze, and we'll take, so when a is equal to 1, we get sine of x, and then plus cos of x, and we analyze with respect to x. Let's add a domain. Let's go from 0. The period for when a is equal to 1 is 2 pi. So it spits out some values, and we get a negative root 2 as the local minimum. So that is a very confusing question. It's worth 1 mark because, yeah, probably not a lot of people will get this. So negative root 2. I'm pretty sure common answer was negative 2, which was actually what I was thinking initially when I saw this question, but yeah, it's negative 2. Yep, so that's basically does it for exam 2. Overall, not bad. Some tricky questions, right? Like this question with the angle, that was doable, I guess. A lot of people should have gotten that. The probability question, most of the probability was pretty standard, besides the final question where you have to do dilations and whatnot. That could be confusing. And yeah, question 5, last question, would have been an absolute headache for some students to wrap their minds around what on earth is going on. But yeah, first question was not too bad, pretty straightforward. So yeah, that does it for exam 2. Hopefully that helped some of you guys. And yeah, good luck for the exam. And I'll see everyone in the next video if you decide to watch more videos.